we're mainly focusing on data parallelism. For data parallelism, there are two types of ways to perform data parallel model training. First approach is called the parameter server-based approach, where each node, or we call each worker, will calculate its own gradient parameters. And we have a server that stores the global version of the gradients. And then each worker will send its own calculation, its own version of the gradients to the server. Server does the average and average all these weights together, and then sends back to each worker, and each worker starts the next iteration. In reality, as you can see, the number of parameters are very huge. One parameter server cannot handle the task. So in reality, usually the parameter servers are breaking into multiple servers. Each server will store a subset of the parameters. And then the workers have to update all these parameter servers before they get back the global states of the parameters. The problem of parameter server-based approach, as you can see, there are so many interactions, communications between worker and parameter servers. And for example, if we given 25 million parameters, let's say each parameter is a float 32 number, and it takes 4 bytes. And then the total amount of communication, the parameters passed is 100 million parameters, 100 million bytes of data. And soon you can see as we scale the number of workers into maybe 16, 32, 64, or even larger, the network bandwidth become a bottleneck because you cannot simply pass so many parameters to the server with even a very fast network today. The second approach is called the Ring-Allreduce based approach. In this approach, there's no servers. All the worker will store a global, store the entire set of the parameters. Each worker work on its own input data, calculates the gradients based on that batch of data. And then when it's trying to calculate the global parameters for the next iteration, what it does is each worker will send a portion of its parameters calculated, the gradients calculated, to the next twist neighbor. So in this example, for example, worker 1 will send one piece of data to worker 2, and worker 2 will send the second piece of data to worker 3. At the same time, while worker 1 sends the first piece of parameters gradients to worker 2 will does the average on its own host. So you can see after 4 iterations, all the workers will get the same set of parameters, which is the average across all these parameters, all these gradients. So this is how the Ring-Allreduce based approach works. And the advantage of the Ring-Allreduce based approach is that the communication between workers is not dependent on the number of workers. You could have n workers, however, at the same time, the communication only contains 2 pieces of the data. Depends on how you partition the gradients, but it's not dependent, it's independent of the number of workers you have. So this way, you can scale very well as you increase the number of workers.
So I think it's like a derivative of MapReduce. So it's all reduced only for average operation, the operation for average.
Yeah, it's all reduced for average operation.
This is what's used for disk beneath. You know, disk beneath.
Yeah, I think that's
ordinary code way to do. Yeah, so I was curious if.
I think in Tensorflow they were using the parameter server approach. I'm not sure about this.
So, any pros and cons compared to these 2 approaches?
Yeah, that's a very good question. As I mentioned, I think the best advantage of using Ring-Allreduce approach is when you have a huge number of parameters that you need to pass between workers. or between workers and servers. So in that case, the Ring-Allreduce approach scales very well, does not have the network bandwidth concern. However, if your number of parameters is not that large, especially in the sparse model, where you don't have that many number of parameters, in that case, parameter server has a better performance. Because we cannot leverage this bandwidth efficiency from the Ring-Allreduce approach.
How about one server down, which one is the
reliability, I think in this case, all the workers will store the same copy of the parameters. So if one worker down, I think that the other worker can still continue work with their own copies of parameters. But for parameter server approach, yeah, I think if parameter server, each server only stores a subset of the parameters. Say if one server 1 goes down, then it loses all the parameters, and then server 2 does not have the information, and it has to all the parameters in this iteration has to be recalculated again. So next I'll give you an introduction of what's Apache MXNet. So Apache MXNet is currently incubating open source project under Apache. It's a framework for deep neural networks, both training and inference. It's created by academia from CMU and the collaboration between CMU and the University of Washington. It's being adopted by AWS as the DM frameworks in November 2016, and it's since been widely used within Amazon. And also Apache MXNet has many contributors from other industries, for example, NVIDIA, Intel, and so on. So Apache MXNet itself, in the backend, it uses an asynchronous engine. So what is an asynchronous engine? So first I'll give you what's asynchronous, synchronous computation. For example, you define some operations in your Python, and then whenever you write some Python operations, asynchronous computation is that we send this operation to the backend. Backend immediately start calculating results, and your front end is blocked until the result is calculated in the backend, send it back, and then you can start the next operation in the front end, for example, Python in this case. However, asynchronous computation is that at front end you specify these operations in Python, but the backend will not really start executing until you are really needing the result from your operator. To give example, for example, you can write Python some maybe a convolution operator followed by a pooling operator, and then you don't really need the result until you finally want to say, I want to start my training, or you want to say, convert this output into, I want to print out output, for example. So that's when, in the asynchronous computation, we can use some operator, for example, wait to read, or some other operator say, convert NumPy output, or print simply. That's the time where the actual computation kicks in backend. And that's the asynchronous engine handling in the backend for the MXNet. So the benefits of asynchronous computation is that it allows more parallelism. Because if you don't have to execute all the computation sequentially, you can just store these operations into a computation graph. And then the engine can analyze the computation graph, and based on the dependency, you can schedule two operations if it has no dependency between each other to execute at the same time. So next is Horovod. So Horovod is an open source framework which currently is under Linux Foundation for distributed model training. It currently supports Tensorflow, Keras, MXNet, and PyTorch, which are the four most popular deep neural network frameworks out there. It's developed at Uber since October 2017, and it's been a very active project till today. So Horovod basically it implements this Ring-Allreduce approach using MPI and the NCCL. For those of you who are not familiar with MPI and NCCL, MPI is a message passing interface to communicate between worker nodes. That's this all reduce or gather broadcast operations. And the NCCL is efficient communication methods developed by NVIDIA, which is very good at communicating between GPUs. It's very similar to MPI, but it's more efficient when it's doing communication between GPUs.
Does it matter which MPI you use?
If you're running on GPU machines and you compile with NCCL, if you have the NCCL on your instance, that's more efficient, much faster than MPI itself.
No, but if you're running between nodes, there's various MPIs.
Yeah.
Does it matter which MPI? I mean, there's open MPI.
Right. I think Horovod has both open MPI and MPI CH, but we don't see a performance difference between
But
those.
just for functionality, the user have to worry about that?
Functionality-wise, I don't think the user need to worry about that.
Okay.
It's taken care of by Horovod.
So the interconnection between hosts using MPI, then within the host, the multiple GPU actually communicate through the NCCL.
Yes. Okay, so this is a high-level picture of how do we integrate MXNet with Horovod. So on the right-hand side shows the current execution flow of MXNet. Basically, we have a model. We send the parameters to optimizer and calculate gradients and update. On the Horovod side, first we need to broadcast the parameters to all the hosts. And then it has a distributed optimizer, which is derived from MXNet optimizer. It's an object wrapped around MXNet optimizer. And then finally, it has the Allreduce operation, which is used to calculate the gradients for multiple hosts and update the hosts update the hosts with the average gradients. And at the low level, this is how we implement this integration. Basically, we leverage the power of asynchronous engine in MXNet. For each operation, for example, the broadcast and Allreduce, we use push async methods to push these actions into the MXNet engine. So the MXNet engine will treat these operations just like a regular computation node. And the MXNet engine itself has a task dependency, can take care of the task dependency automatically without the user intervention. And by doing this asynchronous computation, it can improve the training throughput overall. Because we don't have to synchronize between different nodes in the, for example, Allreduce. Because when it comes to this node, we know we need to get the value out of the Allreduce computation. That's when the MXNet engine kicks in to start executing the entire computation run.
So that bounding box you showed is on one CPU, MXNet engine. Is it on one?
It's on one process.
One process, but it's distributed.
Yes, it's distributed. Each process will have this MXNet engine.
Each process is a copy of the MXNet engine. The MXNet is designed to be distributed right from the software.
Yes.
So only all reduce their code at SU, otherwise other things just later.
Yeah, it's a lengthy evaluation. Only when it reaches the Allreduce stage, then it starts the entire computation run, the MXNet engine.
They will return some value back, or
Yes, it will calculate the gradients and using the Ring-Allreduce to pass the gradients to the other workers around. But that operation is handled by Horovod. That's the Horovod Allreduce action. So this is how Horovod Allreduce actually sending as a callback to MXNet.
then for broadcast, what is return? You already
Broadcast does not return. It's simply just a yeah.
So it seems like Horovod is just like instructions to this MXNet. MXNet is doing all the distributed stuff.
The real implementation is we use MXNet engine more like a task scheduling engine to how to schedule tasks, how to run together. But the real communication is implemented by Horovod. So like an MPI or decode underlying implementation is done on the hardware side. We just send this operation to MXNet engine as a fallback. So we also did a few performance optimization on top of it. So first of all is we use mixed precision. Basically, we use, as we know, if you have a higher precision for training, you get better training accuracy. So in this case, we use flow 32 for training, and then when we pass in the gradients, we down pass it to flow 16 to reduce the number of communications between workers. This way, we can still keep a very good training accuracy at the same time improve the throughput. The second optimization is called tensor fusion. As I mentioned earlier, the main advantage from the Ring-Allreduce approach is that if you have a number of parameters you need to communicate between workers, this is the time where the Ring-Allreduce approach is start to shine. However, if the number of parameters is small, then we cannot really take advantage of this approach. So what tensor fusion does is it will combine all the tensors that are ready to be reduced into one big buffer. So for example, the buffer size we can say is 64 megabytes, I think that's by default in Horovod, is that if you only have a small number of tensors, you will not call or reduce at the same time until the number of tensors accumulated exceeds certain buffer size. And then now it's the time to pass in to do the Allreduce operations. And then by doing this, actually we can see that performance can be improved by 65%. That's very significant. And another is hierarchy Allreduce, which I think is implemented in NCCL. I think it's implemented in NCCL, where when you do the Allreduce, you not simply just reduce all the nodes at the same time, you do this hierarchical way. Or reducing certain number of nodes, and reducing to one node, and then reduce other set of nodes together. And we can see some performance gain from 10 to 30% based on the number of nodes running using the hierarchical Allreduce.
So the Allreduce between nodes is done with MPI's Allreduce?
I'm not quite sure. I think they're similar.
Single node thing, right?
They are similar idea. There's
they're
an MPI hierarchical Allreduce.
So they're combined?
This is actually implementation detail in Palo, so I don't know the exact detail. The last one is called aggregate SGD. Basically, we aggregate multiple ways in a single port optimizer. This benefits to reduce the synchronizing overhead, as I mentioned. When we get the weight, we have to really start the calculation. And this optimization is actually contributed by NVIDIA engineers. They use this optimization technique and submit to the MLPerf benchmark last year. So we are in the future we'll continue to optimizing this MXNet with Horovod. So a few options. First is we can use operators such as batch norm, value, batch norm, add value to reduce the unnecessary data transfer between CPU and GPU. This is also proposed by NVIDIA engineers, and we are collaborating with them at this moment. The second one is actually they provide different layout. Instead of HW provide NHWC, which I think they claim is runs faster in NVIDIA GPUs. Yes. MLPerf is already submitted. I think this is already in MLPerf, but it's not in the official MXNet release yet. We are trying to upstreaming this to MXNet release.
NVIDIA have their own containers,
yes.
So they have their own fork of the MXNet. So in their NVIDIA container, they have some work. They are like ahead of the MXNet public web. So, but they are upstreaming and upstreaming their work.
So the distributed training, has it been measured against different optimizers? For example, there are certain optimizers like there is asynchronous SGD with delay compensation.
Yes.
Has it been measured against such optimizers and seen how distributed training with Horovod works with such optimizers which are built for a distributed setting?
When we running the benchmark, we did try a few different optimizers. We just empirically we found the SGD is the choose the highest, but we did not really go to theoretical understanding of why certain optimizers is better than the other. So here is our benchmark setup. So we use the model which is the Resident 50 version 1B. I think it's the same, have the same number of parameters as the original version. And we're running on the input data sample is from ImageNet, which has around 14 million images. And in our training, we choose the batch. We use the SGD optimizer, and then the batch size is 256. The learning rate is 0.1, and based on one of the papers I referenced there, is that it's a heuristic. As you increase the number of workers, the heuristic is to linear scale the learning rate. This is we just follow the same heuristic to do that. There's no theoretical reason for that, but they find this achieves good accuracy while scaling the number of nodes, number of GPUs. And the number of epochs we choose is 90, which we have achieved accurate convergence at the end. The software we use is CUDA 9.2. We are running on Ubuntu 16.4 OS with the CUDA 7.2.1 and the NCCL 2.2 and OpenMPI. And the hardware we use is we are running on AWS Cloud. For the GPU instances, we are running on P3 16x large GPU instances, which features 8 NVIDIA Tesla 300 GPUs, each pairing with 5,120 CUDA cores and 6040 Tensor cores. And the GPU instances, basically, this is mainly used for parameter servers. We choose the C5 18x large, which has 72 virtual GPUs and 144 GB memories. And the network bandwidth for this setup is 25 Gbps, which is already very, very fast.
So the interconnect is at Infiniband? The network bandwidth is.
I believe so. I'm going to double check.
And when you change the batch size, the effective batch size increases. What does that do to the accuracy?
So this is batch size. Is the batch size per node per GPUs.
Right, but if you were to run 2 experiments, one with just on one node and one on 128 nodes, how would you?
It will actually impact on accuracy, but we also have to adjust the learning rate. I think the learning rate is actually linear to the batch size. It's not the total batch size.
So as a stupid question, do you increase the learning rate or you decrease the learning rate?
You increase the learning rate as you increase the batch size.
You increase.
Yes.
Okay.
So this figure shows the scaling efficiency we observed. The left bar is the one running parameter server. The one in the middle is we running Horovod, and the last one is ideal. How ideal is calculated is based on say what's the throughput we're running on single GPU, and then if you have 8 GPU, the throughput should just multiplied by 8, and if you have 64 GPU, it should be 64. And as you can see, as we increase the number of GPUs, Horovod performs much better than parameter server approach in terms of scaling efficiency. It can achieve 82.6% scaling efficiency at 64 GPUs. And next slide shows the cost comparison. Basically, as we add in extra machines in the parameter servers, we can help increase. So first of all, let me show you this setup. So the first row shows we are running Horovod on 8 P3 16x large GPUs, and the training time is 43 minutes, and that's the throughput and the accuracy. And the cost is calculated based on the we are running on-demand EC2 instances on these GPUs. And the next row shows running a parameter server on the same number of GPU instances, but with the extra 16 CPU instances as parameter servers. In this case, the training time is roughly the same. However, the cost is increased because we need extra 16 CPU instances. The last row shows you we're still running parameter server. However, we don't use extra CPU instances. We call this co-located. Basically, parameter server itself is a logical concept. You can still run server and the worker on the same instances. That's what this co-located means. In this case, even though we are using the same number of instances, however, because the training time is much longer, it even actually costs more than you're running the second parameter server approach where you have dedicated parameter server instances, CPU instances as parameter servers.
Excuse me, these are all on GPU or CPU?
The training,
the
workers is running on GPUs.
Yeah, the nodes, the P3, 16.
P3, 16 extra largest GPUs instances. It has each node has 8 GPU, Tesla GPUs. So the total number of GPUs is 64 in this case. CPU is parameter server only.
So then you have 16.
Yes. This ratio is actually picked based on previous research. They found that using this 2-to-1 ratio, you can achieve the best result running parameter server.
Oh, you see the parameter server is based on CPU?
Yes, it's running on CPU.
All on CPU?
All on CPU, because the parameter server does not need to run any training job. What it does is collects all the gradients and do the average and sends it back.
So, but you are comparing Horovod with parameter server, well, like GPU with a CPU, right?
Just the server is in CPU, but there's one extra node for parameter server.
Yeah.
So you don't need the extra server for Horovod because it does Ring-Allreduce.
So actually, this gives us some sense that reducing the running time, not only just reducing the training time for the user, but also reducing the cost. So here is actually the benchmark, the MLPerf benchmark result submitted by NVIDIA later last year. So their benchmark is on, this is the image classification category. It's also running on ResNet 50 on ImageNet data samples. And the first row is the reference in the MLPerf benchmark, which is running on optimized reference on Pascal 800 hardware. And the Google, this is the result submitted by Google running on their TPUs. And the training time is 11.3 minutes with a speed up of more than 780. And then finally, the NVIDIA actually, they built their own version of MXNet with all these optimization techniques I just introduced earlier in the slides. And they're running on 640 Volta GPUs and achieve the fastest speed in this MLPerf benchmark with a little more than 60 minutes.
How does Horovod compare with this?
This is actually Horovod. This is NVIDIA implementation is the MXNet with Horovod.
What would be the cost comparison between the Google and the NVIDIA there?
So,
unfortunately, I don't have data. The MLPerf did not release the data on cost comparison. They're more just looking for the fastest computation to get out of this.
so the first row refers to Google's TPU,
Yes.
not Horovod, not Horovod.
They are also using Horovod.
They are also using Horovod,
Yes.
TensorFlow.
Because Google has its own distributed TensorFlow serving.
Yes.
They are also using the parameter server approach. They have parameter server approach, but Horovod project started to support TensorFlow in the first place because Uber they use TensorFlow heavily internally, so that's why they started with supporting TensorFlow and was gradually adding the PyTorch support, Keras support, and now we have the MXNet.
So do you know why MN much faster than
This is Volta, it's using Volta.
I guess it comes from both reasons. First of all, is the hardware is different because Google is using TPU and NVIDIA is using GPUs. The second one is different implementation of TensorFlow and MXNet. However, this benchmark is just try all you can to increase the speed, try to come up with the fastest training speed for less than 50. So each company will just try their best to increase the number of hardware to do the training. However, as I mentioned, there's a scaling efficiency. You cannot just simply put more hardware and improve the throughput. There's always a limit where you can reach.
And we're assuming they ended up with reasonably comparable accuracy. I mean, you could train it for
accuracy is about the same. You have to reach a certain level of accuracy before you can actually talk. They're all around like 75, 76%.
But I wonder how that first line Google's, that implementation on Horovod compares with Google's TPU when you train the same benchmark.
So these results are Google running on TPU hardware using Horovod.
But what's the comparison to if it were just Google running on TPU?
Google running on GPU?
No, the MLPerf benchmark on the plain GPU?
Yes.
Without Horovods?
with the parameter server.
I think that would probably be worse because Google is trying to solve the best result there. So probably they did the internal comparison between TensorFlow with Horovod and TensorFlow with parameter server running on their GPU hardware, and this is this will be the best result.
Yeah, basically the MLPerf just gave us. Yeah, basically the MLPerf just show us the best results submitted by each vendor with different setups.
And NVIDIA also tried parameter server with MXNet, parameter server with TensorFlow as well. So the combination of Horovod with MXNet is fastest from NVIDIA.
That's great.
Yeah, so given the same hardware, so how do you compare TensorFlow to MXNet? Assume Horovod is used for both frameworks.
Given the same hardware,
So here I think basically each vendor, like let's say Google, they are going to, because in their Google Cloud they have a bunch of GPU machines, they are going to advertise it. So I don't see the Google they submit results with TensorFlow with GPU, but at AWS we have a TensorFlow team to optimize to focus on running TensorFlow on AWS Cloud and also achieve great performance. So from the talk I had with the TensorFlow team and our deep learning org, I think, can you go back to the previous slide? So we right now we on the same set of hardware. They are running the P360 and large instances. Their training time is like 44 minutes right now with CUDA 10. So right now we are CUDA 9.2. We haven't they said they when upgrading from CUDA 9.2 to CUDA 10, they get like about 5% performance improvement. So I would say we are at the same scale. There maybe sometimes MXNet is a little bit better, but not much if we are comparing with TensorFlow.
Can you comment on the speed of the inter-GPU communication and inter-device communication between
the speed,
NVIDIA and others?
So inter-GPU communication speed between NVIDIA and others.
And network.
I think for inter-GPUs, NVIDIA is usually have the fast inter-GPU communications. So are you saying like inter-GPU comparing to inter-CPU?
No, I meant GPU maybe.
Or inter-TPU. I'm not sure about data inter-TPU because that's probably more Google-specific priority.
Actually, I'm more curious about like these DGX1 machines. Like I don't know. I mean, they seem to be designed for fast inter-GPU communication.
Yes.
How does that differ to the 16 and P3 16X?
It's the same hardware.
Yes,
it's the same hardware.
It's the same GPU. There's some differences in terms of the network configuration. In the DGS boxes, they have InfiniBand versus we have on AWS regular 25 Gbps.
But within the same node, there's 2 quads and there's an NVLink that connects all the 8 GPUs. It's the same class of
only between devices.
Yeah. So once you go internode, that's when the InfiniBand or other networking limitations come into play. But within the same node, there's the high speed NVLink is what they call it, inter-GPU communication.
Next, I think for the download, for example, how to run MXNet and Horovod.
So basically now, thanks for the introduction on the MXNet and Horovod. So now it comes to how we can run MXNet and Horovod together to train our models.
So what version of MXNet do you need to do this?
So the benchmark we done, we are using the master, but the upcoming 1.4.0 release will be able to support training with Horovod.
So we could go through this with 4.0.
Yes.
4.0. Okay.
Yes. Yes. I think we're still holding on the release, but
We're working on it.
yes, it's coming soon. So basically, you need to Horovod is consume MXNet library. So to run the training with MXNet and Horovod, first you need to install MXNet. But there are some limitations. Here is we recommend user to build from source. I know it's gonna take a little bit of time, but we're working on that because of the GCC compiler incompatibility from 4x to 5x. So if you are running our pip package, MXNet pip package right now is building with GCC 4.8.4 compilers. But if you are using pip install and you are on a Linux machine with GCC 5.x, and at the same time you are using the pip package and then you are pip install Horovod, you are going to hit segfault because of the from 4x to 5x they changed the STD function and the function definition, so which causes a runtime segmentation fault. So that's why we recommend user to build from source with the same compiler. So build MXNet and build Horovod using the same compiler if you are on a machine with GCC 5x and above. But right now, Horovod is on the 15.2 release. They are going to release the 16.0 version 06.16 version. At that time, you can just pip install Horovod, which has a MXNet framework supported. Right now, you have to do git clone and the Horovod repo and run a pip install locally against your local Horovod repo instead of pulling the version from the PyTorch server. So, but the usability is going to be improved soon. After you install the MXNet and Horovod and you have your training script ready, you just need to run the MPI run. -mp basically is the number of, not number of hosts, I think there was a mistake there. It's basically the number of the devices, how many GPUs you like to run your, to parallelly training your job, your model. So here is some very simple code samples here. So let's say, assume you already have a training script with MXNet. This is using the symbol module symbol API on the left side, which is performed on the single GPU training. So how you are going to scale and leverage the Horovod to scale up to multiple GPU on the same node or even across multiple nodes. So there are some minimum changes you need to make to your training script. The first is definitely you have to import the Horovod library, and then you initialize. Basically, the Horovod is basically creating a background Horovod project, threads inside your process. So that background threads is handling all the communication between different processes, training processes. And the next one is going to create a context, which is basically where your tensors or where your MXNet operations will be executed. So you use MXNet.GPU and you give the device ID you are going to run. So basically, the Horovod local rank will give you for example, you have 8 GPUs on a single machine. Local rank, each process will have a number ranges from 0 to 7. And then you give the local rank number to the when you're creating the context. So this training process will attach to that GPU device and then push all the MXNet engine operations to that GPU to compute. The next one is you need to wrap the MXNet optimizer with distributed optimizer. Basically, what it does is with MXNet, when you try to update the gradients, it goes to, instead of, if you don't have the Horovod, you just within MXNet compute everything. But when you wrap the MXNet optimizer with a distributed optimizer, all the update goes to the Horovod, and in the Horovod we call all Horovod operations to do all reduce and do the communication between all the processes. And the last change you need to make is basically each Horovod, when training with Horovod, each process will do its own job. And at the very beginning, when you initialize a parameter, we randomly initialize a parameter. But we want every process start from the same point. So that's why we do a parameter broadcast. So when you start the training, each process will initialize the parameter with a different set of values. But we broadcast the value from rank 0 to all the other ranks, other processes. So they have the same set of parameter to start. So they don't diverge much in that sense.
Similar script for accessing Keras/Tensorflow using Horovod or Ring-Allreduce.
Okay.
Yeah. Yes. There is also because we have a TensorFlow with Horovod.
So multiple GPU is still GPU 0. I think there's 1, 0, 1, 2, 3, 4. In the multiple GPU.
Yeah, the local rank itself. When you call you see the Horovod local rank, it will get its. When you use an MPI run to launch multiple processes to train your model, each process will have its own identifier. So the local rank will get you a unique identifier. For example, if I have 8 processes, each process will get 0 to 7. 0, 1 to 7. And
each process get
one number from 0 to 7.
All the local rank is basically the ID of the GPUs. So if you have you usually have 8 GPUs, the local rank is from 0 to 7.
From user, one of the number.
One of them, yes.
Then I need to function 8 processes. Use up 8 CPU.
Yes.
Yes. But that's all handled by the MPI run. So in the previous slides. So the MPI run -MP, you basically specify the number of processes.
So if you have a node with 8 GPUs and you use Horovod, and without Horovod, you get the same performance and accuracy. So for one node, you don't need Horovod, right? But
one node?
One node, right.
Yes, one node. I mean, that question.
You don't need it, but if you use it, you get the same performance and accuracy. Is there any overhead or anything that's?
And we do see in the scaling efficiency chart, we do see some. If you are using when you have 8 GPUs,
right?
The scaling efficiency is like 94 compared to a single GPU. So for example, if you have when you run a job on single GPU, you get let's say 900 images per second. But 8 GPU, we expect to see like 7,200 because 900 multiplied by 8. But the actual throughput we get with 8 GPUs is like, let's say, 6,400.
So we get that 6,400 if you don't use Horovod. You just use nickel with 8 GPUs.
No, but in the Horovod side, with But with 8 GPUs, there is still some communication you need to handle, right?
Right.
It's still not theoretical, still less than theoretical.
I think the
No, but I mean,
question
is there any
is,
performance?
so the performance gain actually comes when you have more GPUs and more
We have more
nodes.
GPUs.
So if you have 8 GPUs, we don't see much performance gain if you use Power. That's true.
Yeah.
But if you scale
But I
up,
mean, you don't lose anything, right?
You don't lose anything.
That's all.
From my
That's
experience,
all.
you don't
That's
lose
all.
anything. You can use raw nickel or Horovod, you should get similar
we can
results.
just run so.
Only advantage is it's easy to scale.
Yeah,
You
right,
can go
yeah.
beyond 8 without changing the way your program's written.
Right, but if you're scaling from a lower number, it doesn't, it sort of warps things, right?
Up to 8.
Right.
You go, yeah.
Only one GPU can allocate to the one process. I think one process can access multiple GPUs.
You can, but in Horovod way, you can.
Oh.
You have to attach each process to one single
So
GPU.
MXNet can one process access.
Yes. In the
So that's why I just.
in the traditional parameter server way, you just launch one training process, and within the training process, you distribute the data onto multiple GPUs. So that is a parameter server way. But in Horovod way, each process will handle one GPU, and they are communicating with each other through the Horovod underlying heads.
So now the machine have 8 processes only.
Yes. So I'm going to show you a demo here.
So because they're separate processes, there's no shared memory, so when they're passing the parameters for the all reduce, they've got to do mem copies. They can't just pass it pointers if they don't have any shared memory.
No shared memory.
Each process store the entire memory of the parameters. Intercept parameters.
But when you're doing the all reduce in the ring, you keep on passing a whole set to the next thing, and you got to do a mem copy there to do that.
Yes.
From some sort of
It's not
IPC.
yeah, they're doing the calculate the average on the memory. There's an in-place updating the.
Yes. So here I want to do a step-to-step demo with you to train a handwritten digit classifier on the MXNet dataset using MXNet with Horovod. So it's we just made some modification on the public tutorial you can access in the MXNet documentation. So we just modify this tutorial to fit into the Horovod case.
But before that, how do you set up multiple machines at the same time? Then all the Horovod those settings.
So basically, goes back to the installation. You just need to perform the same on each node. You need to install the Horovod, so install MXNet library on each host, install the Horovod on each host, and then you can have multiple ways to share your script. For example, you can have a shared file system like AWS EFS to put your scripts there. So each host have access to the same script, and then you can launch the train. Or you can copy the script to each host. Definitely, also you need to load the data into each node.
The same data.
Same set of data. Or you can but you can have a shared file system, right? You can have the data in a shared file system, and all the nodes access the same data. But the performance-wise, that's not very good. So what we did is basically we copy the data into the RAM disk. So basically, we use the template base. So we load the data into the main memory. So we try to minimize the overhead of reading data from the I/O.
Every host will load part of the data.
No, we load the whole data. But in the
we store the entire data in the disk, but then the processor will only load part of the data memory.
Yes. So basically, we divide the data in our data integrator. So we divide the data into the number of Horovod processes And each process have its own index. So each process know which part of the data they're going to access.
So this has transfer type. Also, with no script like I can launch all the hosts at the same time. If this script I have to
you just need to write the script and you need to run this from one host. You
Yes,
specify all the hosts in the host file with just a list of IP addresses.
Yeah, I'm going to show you the later. Let's go run step by step for this example, and I will show you how to run the distributed training on multiple hosts in AWS cloud. So the first step is basically very at the Python program, pull request, you load in all the libraries. So here, the main thing here is you need to load the Horovod import the Horovod library, import MXNet and some modules from MXNet. And then for simplicity here, I just hard-coded some training settings. My data is stored in the minis/data on my EC2 instance. And where the batch size we are training for each GPU device is 64, and we are using float 16 for training. And we just run 5 epochs. So the next thing with Horovod, as I mentioned earlier, you compare to your existing, and if you want to convert your existing training script to using Horovod, you need to initialize Horovod. And after you initialize Horovod, you can set up the context by pinning the GPU to your local rank. So basically, because each Horovod process will have its own rank, and they will attach to a GPU. They are not shared with each other. And after you set up the context, then let's load the data here. So basically, you can see here, there are two. This is partly how we divide. The minis iteration in the MXNet already have the capability to split the data for you. So basically, what you do here, you can see for the training data, we split the whole minis data set by the number of workers. Basically, the Horovod.size will get you how many Horovod processes you launched. And then the party index is basically Horovod rank. So basically, you have rank is a global concept compared to the local rank. So basically, local rank will give you a number, let's say in the P360 in case 0 to 7. But if you have like 16 across 2 nodes, the rank will range from 0 to 50. So rank is global concept, and the local rank is per instance.
So how did you fit an MPI one into the Jupyter notebook? This is a Jupyter notebook, right?
Yes, this is a
Jupyter.
Jupyter.
To use Horovod, you have to use MPI one.
Yeah, this one is a single GPU case.
Single GPU.
I just port my multi-GPU training to this one. It still works. Because basically this is a program that is running for per process. And when you launch when you use MPI run to launch, you're actually running multiple copies of this running separate processes, all right? Multiple instances. So it doesn't matter here. So I don't need to change anything when I launch the multiple GPU training, but this is a minimum set of code examples to run. Horovod.
So HB size equal
to number of processes.
Number of processes.
Yeah. When you MPI run -np the number of processes specified there.
So you have two hosts. Each host has 4 processes, agent equaling A.
Yes. You can do that. So for the validation set, we don't split because we want each process validate on the same on the whole data set to have a aligned validation accuracy evaluation. So here we define a convolutional neural network. It's basically the net. You can also use a MLP to train the minis handwritten digit. So all the information here have detailed explanation here in this documentation. So 2 ways to build MLP layers or convolutional network. So here CNNs give us better performance. So we just use copied the block there and initialize parameters is not special for Horovod. It's same no matter if you don't use Horovod, you need to initialize the Horovod parameters. And this one, this number 7 is specific to Horovod. Basically, you need to get the parameters and then you broadcast. Basically, you specify root rank equal to 0. Basically, you broadcast the value from the rank 0 to all other ranks.
And what's why is there a conditional check? It's not.
Excuse me? Which one?
In 7, web fetch and broadcast.
Yes.
Why do you check if parameters is not none?
It's just for. I think it's just for. I don't find the cases that it's none, but just for completeness, we just write it in the safest way. And then we create the SGD optimizer. And this is a step after you create the SGD optimizer to use Horovod, you need to wrap it with a distributed optimizer such that you can leverage all the Horovod library operations to do the communication between each processes. And after this, you create the trainer and loss function, which is typical for when you're using Gluon API. And then we have a function to evaluate the accuracy, both the train accuracy and the evaluation accuracy. So now we are ready to train the models. So it actually runs very fast and we have great accuracy even in the first epoch. So each epoch on the single GPU runs like every 6 seconds, something like that, 6-7 seconds.
How many hosts do you have?
And this is just a single GPU base. So because setting up multi GPUs with a Jupyter network is not very easy. But this is basically, you can see I run 5 epochs, and in the end I can achieve a validation accuracy about almost 99%.
You say single GPU?
Single
So
GPU.
why do you broadcast? Do you need to broadcast?
I said this is just you don't need to. You don't. So for example, this script I can run with single GPU. I can run with multiple GPU. But with multiple GPU, you need to do the broadcast, right? So I don't want to change the code. Let's say I want to run 1 GPU, I go there and change the code. That's not necessary. If there is only 1 rank, internally we just skip the broadcast. It's just a placeholder there for you to, if you want to scale your training to multiple GPUs, you don't need to change your code.
But in this broadcast, then everything have to do stuff, the same stuff, or you have to do any networking.
No, you don't need to do any networking. You need to do networking because the broadcaster we are using the Horovod broadcast to broadcast parameters across multiple processes. If your process are sitting across multiple hosts, definitely the data will go through the network to reach all the processes.
So you only use storage to take care of that, or?
No, you don't need to. You don't need to. The broadcast is just broadcast parameter is just one Horovod function API. So as long as you install the MXNet, install the Horovod with MXNet support, and then you have this built-in function there.
So you don't have to install the same stuff in there. I mean, all the hosts have to be same stuff in there, or different.
That's an infrastructure setup. Definitely, your instances, all the instances you launched for distributed trading has to be reachable to each other. Otherwise, definitely you can't, right? That is kind of like the more detail of the infrastructure, how you set up your infrastructure. That's another story because there are multiple ways to set up your network, set up your file system there to optimize your trading. So basically, that is a single. I can show you. This is basically the Jupyter network is just this script, which I ported from this script to the Jupyter network. It's the same. You initialize the Horovod, and you create context, note the data, and evaluate, run the train the model, and evaluate the accuracy. So this is basically, I will use this script to run multiple GPU training. An example here. So here are something you need to. So when you run the, so you can see my script here. Which I'm going to run. I'm going to run the training in 16 processes, 16 GPUs. So with 2 nodes. Each instance is a P360 notch. Each has 8 GPUs. So I'm going to launch a training job on 2 instances. So
just for curiosity, can you catch the host file?
Yes, I will. That's what I'm going to do next. So this is the host file. So basically, there are 2 items you need to give. The first one is the IP address. The second, separated by a space, is how slots. It's basically you give how many of GPUs in your machine. So for example, there are 2 hosts there. If you are MPI-run number 4, so because you only launch 4 processes, that 4 processes will launch on the first instances. If you go beyond 8, it will go to the second host to launch additional processes. So that's the idea. Here you specify how many slots. Let's go to, okay, this is my second host. You can see there I have two different IP addresses. This is the first one, this is the second one. And let me monitor the CPU. This is the CPU usage on the second host, on the right side, and the left side I'm going to launch the multi-GPU training there. So let me just copy this example command here. So you can see the only thing you need to specify is the MPI number of processes. I'm running 16, and you give the host file where they are going to look for the instances, how many slots, how many GPU devices on each host. And then there are some other configurations, for example, the minimum number of rings. And next is basically you give the Python, and then where is your script. So basically the glue on minister py has to be accessible on both instances. They have to store it in the same paths. So basically you can either use a shared file system, so you don't need to manage multiple copies, but here I'm just copy there. So now I'm going to launch it. So you can see immediately on the right side, you get their processes, Python processes being scheduled. There are 8 of them. So on the left side, we already all the logins will be directed from multiple different processes. It's pretty fast. Each just 1 minute or 1 second, less than 1 second. Here we are done. So with 16 GPUs, we runs really fast. Each epoch just 1 second, less than 1 second, we finish. So in the end, we can see the accuracy we can achieve is about 98.5. When on a single GPU, we have like 98.7, something like 99. So the accuracy wise, we are still in good shape. But we do see when you scale your training on multiple GPUs, you lose some precision, for example, and the accuracy do get decreased a little bit, but still not much, like a few, like 0.2 or 0.3 percentage. Okay, I think that's for the demo. How to run your training and job with MX and Horovod. And here are some contact information. If you want to get started with Apache MXNet, on SageMaker, if you have any questions, some ideas, how to have questions, how to develop your application using MXNet, feel free to reach us. And here are also some SageMaker, some other services in our AWS deep learning ecosystem, which you can leverage to facilitate your application. So, by taking questions, feel free if you.
Thank you very much.
Thank you.
Really simple question. So the Horovod, how is it transferring information between the different processes of different servers? Is it using protocol buffers or something like that?
It's just API transfer between nodes, and the transfer between GPUs using NCCL.
But for the between the nodes, I should have used terminology. Should have used how? Do you know anything about what it's using to transfer?
It's just API.
MPI. Okay.
Yeah, the MPI library allocate buffers to receive the messages from their peers and then pass along back to the application.
But MPI is using some type of proprietary thing, not like protocol buffers.
Not
like
protocol.
Okay. Got it.
So when after between training, one set the model is just one post, one cannot all the model.
All the workers will save the same model.
You can
the model is replicated
yes,
across the workers.
So basically, what you can do is basically you can save model on from each process. So each process will save one copy of the model.
But will be set. So any
will not be the same because the parameter will slightly be different. So the validation accuracy will you can see from my.
So each process has a little bit different process.
You can see here the tree. This is a epoch number 4.
I think theoretically each process will get each worker will get the same set of parameters. But the difference comes when you do this aggregation. I mean average, because you lose this precision difference. It's more because of that. Yeah. But theoretically,
so you can see each worker the training accuracy is slightly different, but they are roughly at the same size.
I think just one of them.
Yes. Right. You can choose the best one.
Okay. Yeah.
As it's converging, then also the difference between the different processes diminishing.
Will it also be in the SageMaker or just
Yeah, it will be. Yeah, the SageMaker team just I think they just finished integrating TensorFlow with Horovod in their training pipeline. We have already started collaborating on incorporate and integrate MXNet Horovod into the SageMaker training pipeline. But we just merged the work 2 weeks ago. So.
Once official release is out, it will be.
So the data, if you have, say, 16 different processes, the data is split up into 16 different chunks, and each one has its own.
Yes.
So you better be sort of smart about how you split that up, so you don't end up with all of the ones going to the first one, all the twos going to the second one, and
you need to shuffle the data.
We shuffle the data. Yes. Yeah.
So when you save the model, what are you saving?
You save your parameters, you save your symbols, you
The parameters are each
the weights and the biases.
weights, right? But you're doing an Allreduce on the gradients, right?
Yes.
But you have
in the final state, basically what you save, it's like with there is no difference with Horovod. So basically, when you do the training, after you're done, you get your desired accuracy. You save your model to some files, and then you can load the file for your inference. So
but you have 16 different models,
the
right?
model.
You have 16 different GPUs.
No, it's not the same model.
Yes.
It's just simply different replicas of the models, but
they're different, slightly different
in
each one. So
yes.
how do you combine those all
You don't need to. You can just choose the best one.
Okay. So basically, theoretically, each model will have the same parameters. The difference only comes because of the precision
And they were
floating
probably
point
initialized slightly
Right.
differently,
And the
and
model is
they
actually
each,
stored in-
have different training data they were trained on.
Yes.
Right.
So they're
They will
yeah,
be
they're gonna be
slightly
close.
different.
But after Reduce, they should get very close parameters. The model is stored in memory, first of all, in the MXNet. Model is nothing but two parts. One is the structure of the graph. The other one is the weights of each.
So you might also just say process 0 or GPU 0.
Right. When you do the save, you just save the memory, the model in the memory to the file. And
when you're averaging the gradients, it's at the end of each iteration, not
the end of each iteration.
not between layers.
Not between layers.
Not between
Okay, so you wait to iteration.
All the
you
layers,
message.
all from the
Exactly.
end to the input, from the output to.
Yeah. So in the 16, the GPUs, you see the best model. The best model may also depend on the training data
Yes.
locally, right? Yes. So best for himself, maybe not best for other.
But you'll test them all
But
on the
the,
same
but
data,
the,
right?
but my validation set data is the same.
Okay.
I don't,
Oh,
I
validation
didn't,
data.
I didn't split the validation data. That's why I want to get a full sense of how good each model, each copy of the parameters is on each.
And when we say the best model is actually different by 0.1% or something like that. It's very
There
close.
were not much difference. Like, most of them are like within 0.1.
And on the validation, they all came out the same, actually.
This data set
In
is very small.
Yeah.
When you see that, when I train the ImageNet, there are differences. Yes.
Yeah, so can I use different batch sizes on different processes? Because, no, you can't do that? Yeah, because I might have multiple GPUs, but different models. So some are more powerful GPUs and some are less powerful GPUs.
So
GPUs.
to use a Horovod, we recommend to use a harmonious hardware and setup. So roughly each process should go with the same speed.
Okay.
Well, what happens if it's mixed?
If one process finish much earlier than another process, it will just quit, and then the whole job will be cancelled.
There is actually some details on that in the binary training link that was posted on the references. That actually has a situation where the batch size can vary from epoch to epoch, but the accuracy is in the same ballpark. So you might want to look into that blog for some details on that.
I think he was talking about batch sizes from GPU to GPU.
Right.
Instead of epoch to epoch. So if you start with 256 and you run through the whole epoch and change it.
Sure, yeah.
Yeah, that's different. Basically, maybe he has some hardware P2 and P3. P2 instances, the GPU memory, as far as I remember, is 12 gigabyte per GPU, and P3 will have 16. That's a different devices, different capabilities, but we don't recommend that to train with Horovod.
Why the process quit if you? So
basically, it's in Horovod it's a Ring-Allreduce, right? Each process is like a node in the ring. So right now,
it's a serial, right? The first one, second one.
No, they're at the same time.
Oh, they run at the same time?
Yeah. They're not waiting. For example, when they do the Allreduce, at the same time they send one chunk of the data to their neighbor. But at that time the chunk is different. In the MPI case, there is some requirement that all the node has to be there to perform the collaborative job. So if one worker, let's say, finish have much less data, like have 90% of the data compared to others, it finishes much earlier, then it just quit, right? And then all other nodes will quit.
Yeah, but if you have, the nodes are sitting on different machine, and if the communication speed are different from network to network, then you cannot do that.
Yeah, there certainly sounds like the Horovod library.
Yeah, there are different rack or different switch,
I think there's a limitation in Horovod implementation.
Yeah, we actually found this issue, and we discussed with the Horovod project Alex from the Uber. So basically, the Horovod they design in a way they have a
so-called coordinator. So all the ranks, the rank 0 is a coordinator. So all the other ranks will coordinate with the rank 0. If one node is already finished all its job, it will notify the rank 0 that, okay, I'm done, I'm going to quit. And then the rank 0 says, okay, one work is done. Then I will notify broadcast shutdown behavior to all the processes. Even those processes still have some work to do. So that is kind of like Alex was mentioning that it's not because of Horovod, it's basically the MPI. Internally, they're doing the Ring-Allreduce. They don't support some node quit early, so they have to terminate the job.
So one way, the simple way you can do maybe do some synchronization, but then that will sacrifice performance. Yeah. Because that's why they did not choose that, right?
So the Allreduce is not blocking the MPI at the end when it does an Allreduce and it blocks.
Yeah, we do sync at the very
But after each iteration, you do an Allreduce, right?
Yes. Yes, we do sync.
And waits for everybody else. Yep. Then it goes back.
Yes.
Earlier, you quoted 96% efficiency with 1 GPU versus 8 GPU on the same node. Was that with parameter store or Horovod? Or both of them have similar efficiency?
Both of them have the same similar efficiency. Look at the figure.
Yeah. Single node. And that's single node 1 GPU to 8 GPU scaling efficiency we don't observe obvious differences between parameter server, KV store, and Horovod.
Okay. Any more questions? Let's thank the speakers again. And thanks for coming.